The mammalian nervous system is not only one of the most intricate bioelectronic engines, but also one of the most complex self-contained systems known, composing of tens of billions of interconnected neural units. As capabilities in microelectronics have improved to rival it, there's been an increasing interest in how we can read and interact with this circuitry, hence the development of the neural interface. Through these, we can express the desire to understand, influence, and project function, development, health, and perception. To realize these aspirations, one of the most pertinent questions to ask is in the stimulation of neurons. There exist many different routes to achieving this: electrical, optical, chemical, mechanical, and thermal, each with their own subpaths. However, nervous tissue is composed of three-dimensional dispersion of neurons. Therefore, it is necessary for a stimulator to non-invasively interface with the entire space. Whether through limitations of interface dimensionality or invasiveness in others, optical-based interfaces have gained increased attention for their potential in this area. Neurons, there are two primary schema in technology, those where light is biologically absorbed and those where a material absorbs it. The biological side is primarily dominated by optogenetics, where light-sensitive ion channels are genetically introduced. Material-based interfaces are more varied in that the absorption of this light can either generate a photovoltage, redox species, or heat, triggering the stimulation. In understanding the optimal direction for in vivo application, the wavelength-dependent penetration depth of light must be considered. Guided by simulations of light entering through the epidermis into tissue, blue light penetrates less than a millimeter, but as the light shifts towards the infrared region, the penetration depth grows to over 5 millimeters. This region from about 630 to 900 nanometers constitutes the first near-infrared window. Fortunately, optogenetics are typically far outside this window, and photovoltaic systems can damage host cells. Optoelectric or photovoltaic interfaces which utilize generated photovoltages or currents face a unique opportunity in utilizing this range. Conductors suitable for near-infrared photovoltaics, referred to as narrowband cap, are not particularly biocompatible, with lots of arsenic and cadmium in the industry standards. Silicon is a well-established semiconductor for this application, but it doesn't absorb well in the near-infrared region. However, after alloying with germanium, the resulting structured near-infrared absorption is enhanced. Here we hypothesize that silicon germanium thin films with higher germanium content will demonstrate enhanced NIR absorption while retaining potential for photovoltaics. We tested this through chemical vapor deposition of silicon germanium thin films with varying elemental ratios by controlling precursor gas flow rates. We then characterize these films from a materials perspective to evaluate their suitability. The first step in evaluating this structure was to determine to what extent silicon and germanium were forming an alloy and what their morphology was. What we found was that through the manipulation of precursor gas flows, we could finally control the final composition of the film, determined through the deconvolution of silicon and germanium XPS peaks. Once we established that baseline, we began to look at the morphology. In the chemical vapor deposition of silicon germanium, germanium tends to aggregate into clusters that inhibit the optoelectronic performance of the device. So to suppress that behavior, we lowered the growth temperature and introduced hydrogen dilution to push towards bulk amorphosity, indicated by both the SEM and grazing incidence XRD characterization. The target synthesis conditions were identified, the optical properties of the material were examined. Through 6 precursor ratios with increasing germanium content, we saw the red shifting of the silicon germanium absorption band to nearly 750 nanometers, while surpassing the near-infrared 1 window. From these measurements, we also extracted that the absorptivity of the films to perform Tok plot band calculations, which showed a trend of decreasing band gap with increasing germanium content, albeit shifted due to calculation assumptions. Through these successive rounds of synthesis and characterizations, we've shown that silicon germanium has potential for near-infrared neural stimulation with its high absorption and suitable morphology. To extend this potential into an application, though, it's necessary to go just beyond the absorber and design a full device with carrier extracting layers. These align with the band structure of the absorber so as to enhance carrier separation and produce the actual photovoltage for stimulation. For this, we started to move in directions for long-term devices and transient devices, both through different device stacks. As we continue to optimize these structures, we are reaching towards that NIR optoelectronic neural stimulator that can exist as a bulk structure, dispersed, or bonded directly to neurons. In taking that step, we are moving to bridge the long-standing gap between three-dimensional spaces of neurons and modern neural interfaces, completely remote.